Hello everyone, welcome to our final session of the Big Specification workshop. We'll have 3 speakers coming up. Our first speaker will be Jules Villard, a software engineer at Meta working on Infer.
Thank you, Conrad. Congratulations to all of you who made it this far. And thank you for staying here this afternoon. So I'm going to talk about Infer, which is a static analysis platform that we develop at Meta. But it's also open source, so anyone can use it or hack on it. I'll talk about it. So in our PL community, and this week we've heard a lot about software, but mostly a lot of effort is focused on these lower levels of the stack, which are gnarly and complicated, and we absolutely want to get right. So it's only natural that a lot of formal methods focus here. It's also where there are smaller programs that perhaps make it easier to reason about and write proofs for and specifications. But of course, where does most of the code live and programmers? Well, it's mostly in this upper layer, and this isn't nearly to scale. And wouldn't it be nice if we could do something for them as well, besides proving that the stuff they build on is correct and beautiful. So what scale are we talking about? Well, for instance, at Meta, we have millions of source files in varied array of languages, thousands of programmers who are writing commits continuously, new code ever-changing, and ever huger. So that's the sort of things we'll have to deal with. And so coming back to the tagline for this week, which is specification, proof, testing at scale, what does it mean for programmers? Can they specify their programs at such a large scale? Well, as Sasha and Xavier made the point earlier, kind of, if you can accept that types are a specification of programs at scale. So, and at Meta, we do a lot of that. So in particular, we use already typed languages to some degree, like Java or C++, but even our dynamic languages, which traditionally have resisted types, are now almost all typed. So it's not terribly good colors, but this is the hack type system, which was developed on top of PHP, and now it's its own language. But that was a huge migration. Tens of millions of lines of PHP are now fully typed. We did the same thing with Flow just a bit later, with JavaScript a bit later, with Flow, but the TypeScript as well. And then the same thing again with Python, and we have Pyre. These 3 tools are written in OCaml, by the way, which is great. And we did this once again with Erlang and the equalizer type system. And meanwhile, even Java got more typed with Kotlin. We got rid of some null errors sometimes. So kind of, there's been a shift in the last decade or so in the programming culture, I feel, where developers are more accepting of writing these types, these tiny little specifications at function boundaries, because they accept they get something else in return. What about proofs? Well, that's a tougher sale. So first of all, programs have bugs, which might not surprise you if you've ever used a computer or a phone. So there is no proof for programs. Also, any proof would have to be fully automatic with almost no specification, because programmers have written types already that tie on now. And what about the last theme, testing? Well, sadly, I ran out of space on the slide, otherwise I would have said lots. So let's talk about static analysis instead. The kind Infer does is interprocedural static analysis, which I think complements types and testing nicely. It's still fully automatic, so no annotations in the code whatsoever, but still it's trying to check deep properties of the code. So interprocedural properties that involve many functions, possibly in many files across your system, that humans would have a terrible time thinking about. And maybe in some way it does proofs at scale, and we'll come back to that. So just very briefly, what is Infer? What does it do? So here's a Java program, and here's a Go function. And if you run Infer on that, what it would do is we see Go calls foo calls bar, which returns null, puts it into A, so A is null. Then call baz on A, and baz dereferences A, so Infer will yell at you and say null reference at this line and give you this little trace replaying that reasoning. And this is just 2 files and 4 methods, and already it's quite a long thing to say, but Infer can dive through much larger pieces of code. So that's what I mean by deep static analysis. And so it does all this at scale quite fast while chasing these properties. And so more generally, Infer works on a range of languages, from Java to Clang-like languages to Erlang. People at Microsoft have written a C# frontend, well, really a .NET frontend. Some other people have written Ada frontend. We've added Hack and are adding Python to this picture. And on the other end, the output is a bunch of different bug types that Infer looks for. There's tens of those, but amongst them are memory errors like null dereference or resource leaks. There's data races, deadlocks, and some more funny ones like unnecessary copies in C++ or asymptotic complexity increases. So what are our requirements for static analysis at scale here? So we need to run on all that code that I was talking about earlier. And there's broadly 3 surfaces you might run. One is maybe daily runs that produce batch batch reports on all your code. Historically, we've mostly focused on code review time, so running in CI and commenting on pull requests like human reviewers would do, flagging up new errors. But these days, we're also running in the editor for in shallower runs and maybe shallower properties. So that's scalability in the sort of traditional sense, like gotta be fast. But there's other dimensions of scalability at play here. In particular, we want to handle multiple languages, and we have to be able to add more languages in a somewhat reasonable time frame. Right now, it maybe takes us a year or so to add a language in a convincing way. And scalability in the properties we check. So it must be easy for us to add new checkers, new types of issues. In particular, when developers come to us with big problems like, oh, I can't sleep at night because this thing is good. My code base is riddled with this kind of problem. Can you help us, please? And said that already. Oh, yes. And so again, we're in this big scale thing, but it's only 8 of us. So that's why we need these last 2 pieces of scalability to make our lives easier. These colors are awful. So in this talk, I talk a bit about the various pieces of Infer that make this work. And in particular, I'll focus on, I guess I won't spend much time on this part because I'm under pressure from Big Spec to finish my talk in 30 minutes and not 45.
You do have the 45.
Oh, I do have the 45. Okay. So you get the full shebang then. So we talk a little bit about the intermediate representation of Infer that underpins a lot of the power in dealing with various languages. Because all these front-end source languages compile to the same IR, and then the analysis at the other end only have to care about that small IR. And so then I explain how we can write this analysis in a very nice, very natural way. So let's talk about the intermediate language, which is called CIL. So CIL is a CFG of instructions, basically. And instructions are really just these 4 kinds of instructions: load from memory, store to memory, just an assume statement of some kind, and call a function. And that's it. That's all your analysis has to care about, and some metadata if you want. So from a front-end writer perspective, writing basically a compiler from your source language to CL can be quite hardest. It's very, very low level, but also the data structure itself, the OCaml data structure, is not very friendly for front-end writers. It has lots of repetition. It's difficult to set up. It has some unclear invariants that analysis have come to expect from the original front ends that now new front ends have to obey as well, but nobody knows what they are exactly. For instance, that's the type of variables, like the very basic building block of instructions and expressions. And a variable is a whole bunch of things. You have to fill in God knows how many things, and in particular, you have to give it the procedure name of the procedure you're in. So that's part of the repetition and the unpleasantness. So what we developed in recent years is this new intermediate front end we call textual, which is sort of the minimal amount of information needed to actually recreate the full CIL. And so that's one nice property about it. Another nice property is it can be emitted outside of Infer, so not from OCaml, you can write text directly. And for instance, notice here, the variable is just a name. It doesn't have this crazy complex structure I showed on the previous slide. So we use that to write a hack frontend at breakneck speed and a Python frontend as well. And that's all I'll say about the frontend part. So if there are any questions, yes?
So does CIL have to represent all the source type information?
Yes, excellent point. So CIL is actually two parts. There's these instructions, but there's also on the side, there's what we call type environment, which is the class hierarchy of your program, in particular, if it has classes. In C, it's just what fields are in what structs. So it lives on the side. You can query it from your analysis. Cool. So that's it for that. So it's sort of a platform for front-end writers in that sense. Yes?
Where in the previous thing can I saw somewhere there are different kinds of specs that you can, different sorts of things you can check for, races, what have you.
Right.
Is there a way you can sort of customize things at the SID level? Does that make sense? Is that extensible in some way, or?
Okay, so obviously this is all a big lie, and it's not true that you write all your analysis on top of CIL and you completely ignore the source languages. There are some things you need to do to handle new languages. So in particular, if you talk about data races, if you add Java support, you have to know what a lock is and what it looks like in your language. And so you add what we call models so that you can recognize them in your analysis. So there's a little bit of delta for each language. In practice, it's really the vast bulk of this analysis is for all languages, and then there's some small things for each. But it's not negligible, and it's a lot of work writing all these models. So to write new analysis, we have this abstract interpretation framework, and that we found quite handy. So let's go to the front end again. So we start from some source code in C, for instance, and Infer will translate that to a CFG of CIL instructions. And your analysis, well, first, it's already nicer to deal with this than that, but that's not even what you have to deal with. You only need to provide very few simple ingredients to this AI framework to get a full-fledged analysis. Sorry. So what are the ingredients you need to provide? You need to say what your states are, what your abstract states are for your analysis, for your abstract domain. In particular, it will have an empty state at the start. And then as you go along, the AI framework will schedule your analysis intra-procedurally on those nodes according to various schedulers you can pick from. So here, for instance, we're going forward. And so it will give the empty state to your transfer function on the first instruction. and then it will schedule the transfer function on following nodes, etc., etc. And all you have to provide is this how one instruction affects your abstract state. Then you need to further specify your domain with a join operation for when you have join nodes in the CFG. And finally, when you have loops, instead of join, we'll call your widen primitive with the number of loop iteration as argument as well. And so if you give these ingredients, shake, and then what you get is an intra-procedural analysis that works on the source code, the real source code, real programs, and will run on your big programs already. So very, very, very simple to get started here. So for example, here's a very simple liveness analysis, your basic program analysis 101 liveness. So your domain is a finite state of variables, and we provide some constructors for abstract domains that make it very easy. So here we just use finite set, which already exists. And then the transfer function is what you'd find in a textbook. So when you're overwriting some variable, you remove it from the set, and you add whatever you read, and that's basically what this whole does for the various instructions. And then at the end, you say, by the way, I want my CFG to be a backward CFG over the CFG with exception edges as well. And my checker is going to be the strategy for walking over the CFG is going to be backward reverse post order, which would really be called just post order, I guess. And so going backwards from the exit node. And this is, so this is actual Infer code. I've doctored this only a little to remove exception support from the code, but it's pretty much what we use. And we use it to know when variables become dead, to tell other analysis that they don't need to care about them anymore. And we use them also to detect dead stores where programmers wrote to a variable but never read the result. So very small analysis, already helpful. Right, so what happens when you want to go inter-procedural, so handle function calls? So the way it works in Infer is very crucial. It works with summaries. So you're analyzing a function foo, and it calls a function bar. What Infer will give you is a mechanism to pause the analysis of the current function and go analyze bar instead, which will produce a summary of bar with your analysis. And then in foo, you're not really allowed to look at bar directly, but you can. What you get is this summary, and you have to use that to compute the summary of the current function. And if you'd already computed the summary of bar earlier, it was stored in the database, so you don't recompute it a second time. So it's a very powerful mechanism. It constrains what kinds of analysis you write, or it constrains the way you write them, because there has to be a lot of contextual information in that summary so that it's good enough to be used in any calling context. So what that looks like for analysis writer is we give you this new primitive that magically gives you a summary if you give it a proc name. You don't have to worry if it's already been analyzed or not, or about pausing your analysis to go do that. It's all handled for you under the hood. So if, for instance, in our CFG before, here we would go analyze on this callee and get a summary back. What you need to provide is a way to turn an analysis into a summary at the end of your analysis. For most analysis, this is basically returning the state at the exit node if you're going forward, or the start node if you're going backward, and a way to incorporate that callee summary into your current state. So given a summary for a new node here, okay, how does it affect the abstract state? So a way to execute summaries, basically. So if you're able to write your analysis in this fashion, then, so the fashion being, you can only analyze one procedure at a time. You're not allowed to look at the calling context of that procedure, and you need to produce a summary. And to do so, you're only allowed to consult other summaries, and you do that automatically. Then the Infer guarantee is the analysis will scale, and it can also start anywhere, because it has this very nice property that because it's bottom-up in a way, you can start it anywhere. You don't need entry points. You don't need to write a harness. So you can analyze fragments of code really easily. Yes?
What's Infer doing to assist with the call graph construction and resolving the target of a call, perhaps, with methods or anything?
That's going to be mostly on your analysis to do. And Pulse does a lot of work to resolve calls, so you can build on top of that. I'm going to talk about this. But at the basic abstract interpretation framework level, what you get is calls resolved by the front ends, as resolved by the front ends, and some of them might be virtual calls. Yes?
So how do you deal with recursion, in particular mutual recursion?
Right. Very naively at the moment. So that on-demand engine that schedules analysis of call E remembers the stack of current recursive calls, and if you're trying to analyze something already in that stack, you get an empty summary at the moment. There's not that much recursive code out there. But yeah, I mean, you could imagine, it's not a fundamental limitation at all. You could easily imagine going a few times around that, or trying to compute a fixed point, do the proper thing. Peter.
My hand is only sort of halfway up, because I didn't understand the answer to Nick's question. If you have some C code with function pointers, or virtual mapping.
Yes, hold that thought. I will come back to function pointers later. Okay, for that you need Pulse. So we have sort of another platform within the platform, which is this Pulse analysis. So Pulse is an analysis for memory, is a memory and value analysis, and it's sort of easily extensible to write more things inside it. And you want to do that instead of using the stock AI framework whenever your analysis cares about path sensitivity, basically, whenever it needs to know about what values things have or what the memory looks like. So as soon as you start pulling on those threads, you're going to have a very hard time developing your own analysis that does that without reinventing almost everything that's in Pulse. So you can build directly in there. And it's built right now as a bug finder, not a prover. So it's been co-developed with incorrectness logic. So it enjoys some no false positive theorems and some principal way to think about reporting issues. So we'll talk a little bit more about that near the end of the talk. Okay, so how do you write one of these compositional interprocedural analysis that works only with summaries? So separation logic gives you a great way to do that, being compositional itself. So more specifically, by abduction technique in separation logic. So this is just a brief introduction to that. So let's say you want to analyze this function foo. Doesn't do much. So you start with no hypothesis, so empty state, and you just start executing forward. And here, to execute this instruction, we need x to be allocated. So what we'll do is we'll say, no problem, x was allocated from the start. I've abduced that x must be allocated at the start to run this function. After this instruction, it points to 0. Then I encounter this instruction. So what do I do here? Same thing, y should be allocated from the start, and it's not the same as x, it lives separately from x. So I know x is unchanged and y points to 42. And then I get to my function call. And I already know this summary. Either someone gave it to me or I computed it independently. And I need to apply it in this state. So I resolve a by abduction query to find, so this is my current state, and I need to find a missing piece I can add to my state so that I satisfy the precondition and maybe some leftover state. So, yes?
When the node point and interpoint have the same type, they are currently different types, so you can probably assume that they are separate node alias. But if they are same type, is it safe to assume that they are node alias, or what do you think?
Ah, thank you very much, because I needed that for my next slide. So,
Okay.
so we'll see. So right now, we would just fail because when we analyze functions, we optimistically assume, unless we know otherwise, that pointers are not aliased. Yes.
Is there some heuristic in place to infer that particular formula? I mean, you could have inferred,
This one?
The precondition. You could have inferred, for instance, x dot next equals 0, 1, y points to underscore. That would have been weaker than this one.
Sorry, you say that? X point to.
So when you were saying you were going to infer something, ownership on y at the assignment of star y equal 42.
Yes.
You were going to apply abduction to infer that the precondition must have y points to underscore, but that's not necessarily the weakest one. So what heuristic makes you choose that?
The heuristic that pointers are separated unless I know otherwise.
Well, so here's another candidate. It could have been x dot next equals 0, 1, y gets y points to underscore.
Ah, right. Yes. Well, we don't do that because no one knows how to reason about magic ones automatically.
So you will never infer a 1.
No.
Are there other heuristics like that in place?
Yeah, tons. But I mean, it's basically the algorithms described in the original by abduction paper and the incorrectness separation logic one. But when restricted to the conjunctive fragment of separation logic with symbolic heaps, basically.
More stupidly, why distinct from X?
Yes, so that we come back to later. It's just a heuristic. It's just it's just a choice. We could create two specifications, one with aliased or not aliased, but we would quickly explode. So we don't want to do that, and we optimistically assume this one. We think this one will be the most useful one that will be able to reuse at call sites the most. But stay tuned because that's not the end. Okay, so I do my by abduction, I infer some other states, and I finish my proof. And now that I've been perfectly set up for that, let's go to what happens with aliasing. So let's say I have a function that touches two cells. I foolishly infer this two-cell specification, but then in a call site, I actually call that function with twice the same cell. So I can't apply this precondition because z points to blank, star z points to blank is the same as false. So instead, what we will do is we will break our promise and we will reanalyze foo, given our new precondition that x is equal to y. So we reanalyze foo, we get these second specifications for it, and now we can go forward. So we can handle, yes?
You keep both summaries.
Yeah, we keep both summaries, and we can accumulate a number of them like this, or if you have more possible aliasing. You can use a similar technique to deal with function pointers. So we don't have higher order specifications, so we won't give a spec to invoke that it calls whatever spec f has. And we don't want to get into that business. We like our simple first order specifications. So, but we can still use specialization to handle these sort of examples precisely. So let's go through what Infer would do to analyze this boo function here. It will see a call to invoke, go analyze invoke. So we don't know what f is or what I is. But here when analyzing invoke, we'll realize, oh, I'm calling this value, I have no idea what function it is. So the summary for invoke will have a note somewhere that says, by the way, if you know what function f is, reanalyze me, specialize me. So Boo will see that, say, wait a minute, I know who f is, it's this increment function here, so let's go. So we start again with a new precondition where f points to anchor, and then we can go analyze this and get a nice specification for invoke specialized to increment. And we can use that here, realize that this is 1, and so that we cannot get to the error, and we avoid reporting a false positive. Everyone's very happy. Yes?
One might worry that this kind of reanalysis with cascade can't be expensive.
Yeah, one might worry that. I think one argument is if you're making many invocations to many very different behaviors like this, there's no escaping analyzing these different behaviors. So you still scale sort of as the program scales. And the other more pragmatic answer is we bound the number of specializations to some bound as well to make sure we don't go too crazy. But also in practice, this barely makes a noticeable difference in performance. So this happens very rarely compared to the normal case.
Is that because people use function pointers and inheritance and things like that less than the textbooks say?
Maybe, yes. Yeah, some of it is a bit mysterious to us, but yeah, not every method call is virtual dispatch, and not every function call is a function pointer.
Almost none of them are.
Yeah, a few of them are.
We have statistics, tables, and data.
Under?
I mean, so apparent. So I think so. What's been discussed is actually a major driving factor of what you implement in the analyzer.
Yeah.
Do you do vanilla or do you go deep? So probably you'll skip and supersede these numbers. Can you share some of them?
Yeah, I wish I had them, but yeah, it's not huge. And one reason might also be we never get quite high enough in the program near the top level where those types are actually given, and you actually start to specialize en masse the code below. So that could happen as well. When we stay very local, the code works for. And one thing we never do is we see a virtual call and then we start saying, oh, it could be any of these 100 methods. Like we'd rather do some treat this as an unknown call that starts enumerating possibilities. So compositionality is really crucial to the way Infer operates. Separation logic is a great way to be compositional. And when it's not such a great way, that's fine. We have an escape hatch now, which is specialization. It's not very scalable in theory. In practice, it's okay. And we use it. I showed aliasing and function pointer. You can do dynamic dispatch as well. You can say, oh, I didn't resolve this virtual call. Maybe if you know what the concrete instance of that argument is, analyze again. Cool. So there we have it. We have an analyzer. You give it a program. It computes a whole bunch of whole triples for each procedure. So we've done all our proofs at scale. Job done. Cool. But really, what have we computed here? So we compute an over approximation of things. So whole triples compute some over approximating property of the code. The way the Infer would run is try to prove the program has no bugs, compute whole triples for millions and millions of functions, and then the proof fails, of course, because, again, the program is not correct by any stretch of the imagination. And even if it were, it's very unlikely you could prove it correct automatically with no annotations. So the proof will fail, but then what value does it, what good was it to run Infer? Like, is someone going to go look at those whole triples one by one and check that it makes sense or inform them somehow? No. So instead, you use the proof failures to report bugs to developers. So you're using very sophisticated proof techniques that try to establish correctness, but in the end, all you do is find bugs. So with that in mind, the value of having this proof mechanism is unclear. So especially since if your only goal is to catch bugs, then over-approximation might not be what you want, because you might find false positives that live only in your over-approximation. This is the same point a third time. So instead, what we've shifted towards in recent years is more towards under-approximation, which gave rise to incorrectness logic. So in under-approximation, we're only computing real behaviors of the program. So this time, any bug you find in your abstraction is going to be a true positive. It's going to be realizable by the program. But what's the catch now? The catch is you can have more false negatives than before. Of course, before you could also have false negatives, because after you've discovered many proof failures in your program, you filtered a lot of them out before reporting only some of them as bugs. So the nice thing about this is it gives us an easier recipe to make abstract domains. So in Pulse, our base states are basically separation logic formulas, which means, but precisely we have a list of pre and post pairs, like I showed in the bi-abduction, with a pure path condition. And we get those with bi-inductive inference, and there's a custom SMT solver to figure out if things are unsat. And or join in our domain. When you're designing abstract domains, you have all the cleverness and all the brain power of the community is how to design a good join that doesn't lose too much precision. And here we completely bypass that step. And we get a lot lazier, and we just use disjunction instead. So very easy to get started. And for widening, there's also a very easy answer, which is to do loop unrolling a finite number of times. And that's valid under approximation. So the benefits, it's simple, makes my life easier. And since it's under approximate, we never ever have any false positives. Right, Nick?
According to the papers.
Okay, so little asterisk there. So of course we still have false positives. But I mean, it still sounds with respect to some semantics, which may or may not be the semantics you want. So the caveats are, of course, there are functions we don't have the code for, we don't know what they do. We have some heuristic to deal with them. The sound thing to do would be to bottom up at these functions and stop the analysis. But if we did that, we'd have terrible coverage and wouldn't be very useful. So we don't. So we have some heuristics to havoc the state in some ways, be conservative, try to not introduce false positives, but it's very difficult. Another way we deal with this is by writing models for specific unknown functions, like functions in standard libraries, or functions you really, really care about in your code. The solver doesn't really know about integers. It solves everything in terms of rationals. So if you wanted, so it lets some pass through that shouldn't. Pointers in C, notably, are just integers. They're not the true C memory model. The SMT solver is custom and incomplete, especially outside of linear arithmetic. And we don't handle concurrency, which most of the time is a fine under-approximation of reality, just run sequentially. But sometimes you actually rely on concurrency to know you can't get into some states. So as a bug finder now, the way Infer works is a lot more straightforward to explain. We compute incorrectness triples for each procedures, and we report bugs that are true bugs, asterisks. But the bugs are driven by this incorrectness logic, which has them as first-class citizens. And the catch now is we can't prove there are no bugs. So that's our previous story, and lo and behold, our new story is just prove programs have bugs, and then report those bugs. So that's pretty much it. So gave a little tour of these green parts. And we build Infer in a sort of platformy way for our own sake and sanity, so that it's easy to add language frontends, it's easy to add new analysis, and it's easy to do sophisticated analysis on top of parse. And what I really want to convince you about is that at scale, bug finding is sort of correctness is bug finding almost, or at least bug finding is our way to bring proofs to the masses at scale. The other takeaway is compositional analysis scale for free, so write compositional analysis. And the Infer platform is pretty nice to work with, if I do say so myself, so you can experiment with it, and bonus, you get to analyze real code very easily. Some random challenges I didn't think very hard about. So under approximation is still difficult because it's all well and good to do finite unrollings, but that doesn't get you very far. It would be very nice to have a way to summarize loops that would let us get past loops, but the only way I know how to do that is by being over-approximate. Array reasoning is hard because separation logic is all well and good for pointers because pointers with different access paths are often disjoint in practice. That's not true at all with array indices, so there's no really good way to have local reasoning here. So it would be neat to have array reasoning in Infer. And yeah, and the other challenge is what to do with everything Infer computes. So we compute a large amount of things, and in the end we report very little pieces of information, like just a few bugs, amongst the megabytes of data we computed. So we inferred tons and tons of specs. Some of them are both over-approximate and under-approximate and would be fine correctness specs, but we don't care. And more generally, how do we exploit this wealth of data we learn about your programs beyond reporting bugs? Something LLMs, yes. That's it. Thank you.
The next talk is a little shorter, so let's just do a couple of questions.
This was super cool, thank you. I'm wondering if you can say a bit about maybe elaborating on the question that you asked earlier, what to expect. If I put Infer on stick it on my 10,000 line C# code base, what should I expect? How fast will it run? How many bugs do you typically report?
How many bugs you got? It runs pretty fast. We aim to run in roughly the order of magnitude as compiling your code, like twice as slow maybe. Maybe 10x as slow. Depends. Yeah. So it runs pretty fast.
Is there an incrementality story? If I do a fix and I run it again, does it start from scratch?
Kind of. Yes, there is incrementality. It has some soundness issues, I think, but it mostly works. We don't use it.
One more question. Oh, sorry. Peter, was that a question? Let's go with what we selected. Go.
So you mentioned that integer pointers are a source of
non-under-approximation, does that mean you sometimes find bugs that rely on illegal C?
That's a great question. I didn't think that much about this. Is it even a source of under-approximation? It's just a discrepancy with models you might expect.
Okay, to be fair to our speaker, let's move on now. So our next speaker, so firstly, thanks Jules Villard for the talk.